Hi, everybody. So, in today's video, we are going to be talking about solving differential equations, which is what we've already been doing. And we are still going to be discussing finding general solutions as well as finding particular solutions. Today, we're going to be using a very similar process to what we discussed in our previous video. It's just that today, the problems that we're solving are going to be a little bit more complicated. So, we're going to be following the same procedure. Step one is always going to be to separate the variables. Step two is still going to be to integrate on both sides of the equation. Because as we discussed previously, an integral is the inverse operation of a derivative. You do the opposite thing. So by doing an antiderivative, we are able to find the original problem using a derivative equation. We are going to write plus c on one side only of the equation, and we'll discuss that again today, how the constant only needs to go on the right side. And last but not least, we are going to solve for or plus your c if you have an initial value. So as we discussed before, if you actually know the initial value, you can actually find the value of c that is specific to that particular solution. If you don't, you can't find that initial value. Finally, and this is the part that's going to be a little different today, sometimes we are going to need to solve for y. So sometimes at the end of this problem, the y is not going to be by itself, which is something we haven't really seen yet, and that's what makes today a little bit more complicated. When the y variable is not alone in your final answer, you need to get that alone. So that's going to be kind of the new extra step of the day. Let's go ahead and take a look at problem one. So this is a very similar problem to what you might see as part of an FRQ on the AP test. It says, suppose dy over dx equals 3xy. Find the general solution to the differential equation y equals f of x. Then find the particular solution if f of 2 equals 1. So in order to find the general solution, which means your answer has a plus c in it, we're going to take our differential equation that we were given in the original problem, and we're going to separate the variables. So step number one is going to be to get the x's on the right side and the y's on the left side. That was not a very straight line, I apologize. Now, in order to do this, we need to realize that unlike the problems that we've seen previously, in this differential equation, we have a y and an x on the left side, and we also have a y and an x on the right side. So if we multiply by dx on both sides, we end up with dy equals 3xy times dx. In the past, that was enough to get our variables separated, but in this problem, that's not going to be enough because we still have a y on the right-hand side. So now what I'm going to do is I'm going to divide by y on both sides. The new equation that I have then is going to be 1 over y times dy equals 3x times dx. So it was a little bit more work than in the past to get the variables separated. Now, step number one here is a really important step because we're not going to be able to integrate if we have x's and y's mixed together. And step number two is to do just that. It's going to be to integrate on both sides. In our previous examples, we always just had a dy over here, and we said there was an invisible 1, which is why the antiderivative would just be y. In this problem, however, we don't have just a dy. We have a 1 over y. The antiderivative of 1 over something is just going to be the natural log of the absolute value of that something, of the absolute value of y. Now on the right-hand side, we're going to be looking at the antiderivative of 3x. So I would add 1 to the power, which makes it an x squared, and then divide by my new power, which makes it a 3 over 2. At the same time, I'm going to put a plus c on the right-hand side only. That's basically the first 3 steps to my process, and at this point, I have a general solution to my differential equation. The next step is going to be to find the value of c if possible. Since we were given f of 2 equals 1, I can use the given x and the given y to find the value of c. So to do that, and I like to draw a line here to show like I'm taking a little bit of a detour, I'm going to plug in the y. So the natural log of the absolute value of 1 is just 1. So I'm not going to keep the absolute value anymore. I'm just going to change it to a 1. Equals 3 over 2 times 2, which is the x-coordinate of the initial value, squared, plus c. Now, one of the things we need to know here is that the natural log of 1 is 0. So we end up with 0 equals 2 squared is 4, divided by 2 is 2, times 3 is 6. So 6 plus c, which means c should be negative 6. That's kind of a detour to find the value of c, and now what I'm going to do is plug the value of c in. So using this information, I know that the solution to my differential equation is that the natural log of the absolute value of y is 3 over 2 x squared minus 6. Now remember that I said the extra step here is going to be to get y by itself. So step number 5 is going to be to take this equation and isolate y. So this was step number 4. Take this equation and isolate y. In order to do that, I need to undo having a natural log here. Since the inverse operation of a natural log is e, I'm going to e both sides, which is not probably the mathematically correct way to say it, but basically I'm raising e to the power of the sides of the equation. When I do that, I get the e and the natural log undo each other. They're inverses. So I would have the absolute value of y equals e to the power of 3 over 2x squared minus 6. Now, an absolute value, when you want to get rid of an absolute value, you need to use a plus or a minus because an absolute value always has two solutions, a positive and a negative. For example, if I know that the absolute value of x is 7, then x could have been positive 7 or negative 7 because the absolute value of both positive and negative 7 is 7. So in order to get rid of the absolute value, we need to do plus or minus e to the power of 3 over 2 x squared minus 6. Now the conundrum that we have is that we can't leave our final answer with a plus or minus. So what we do next to determine whether we want to keep the plus or keep the minus is we go back to our initial value. We know that when we plug in the number 2, we want to get the value positive 1. The plus and the minus are going to give me two different final answers. So the way we check to see whether we want a plus or a minus is we test the initial value to determine plus or minus in the final answer. So if I take the number 2 and I plug it into my final answer, 2 squared is 4 times 3 over 2 is 6, 6 minus 6 is 0. So if I test this, I get plus or minus e to the 0. Now e to the 0 is 1, which means I'm either going to have plus or minus 1. Since the initial value says that y should be positive 1, I know that I don't want the negative. So my final answer here, I'm not going to use the negative, I'm going to use the positive version. So e to the 3 over 2x squared minus 6, and I'm not going to have plus or minus, it's just going to be the positive, and that's my final answer. This whole side over here is kind of the new piece that we're adding today. The other stuff is all stuff that we kind of did in the past. This is the new piece, the solving for y at the end. Let's do another example. So in problem number 2, it says, suppose dy over dx equals x squared over y. Find the particular solution if f of 1 is negative 1. So again, find the particular solution, which means figure out the original equation if this is the derivative. And in order to do that, I need to start by separating my variables. So step 1 is to separate the variables. So dy over dx equals x squared over y. Now, in this case, I'm going to try to do two steps at once, if that's okay. I'm going to actually multiply by y on both sides, and I'm also going to multiply by dx on both sides at the same time. That's going to make the y's cancel and the dx's cancel, which means my new equation is going to be y times dy equals x squared times dx. Now I've got the x's and the y's separated. Step number 2 is going to be to integrate on both sides to undo the derivative. The antiderivative of y would just be 1/2 y squared, and the antiderivative of x squared would be 1/3 x cubed. And at this point, I'm going to remember to put my plus c. Now, this is where I like to take a detour. So I'm going to take my initial value, my given x and my given y, and I'm going to plug them in, and I'm going to find the c value. So I would have 1/2 times -1 squared equals 1/3 times +1 to the third power plus c. Now, -1 squared is just 1, so I have a half equals a third plus c. And if I subtract 1/3 on both sides, c would be 1/2 minus 1/3, which is 1/6. Once I have my c value, I'm going to plug it in to my equation and I'm going to write my new equation. So I'm going to have 1/2 y squared equals 1/3 x cubed plus 1/6. Now from here, I have to kind of do what I did on the other page, which is get y by itself. So to undo 1/2, I'm actually going to multiply by 2 on both sides, which means I'm going to get y squared equals 2/3 x cubed plus 1/3. I'm just distributing that 2 to both the 1/3 and the 1/6. Then I'm going to square root both sides to undo the squared. But again, it's important to realize that a square root really has two answers, plus or minus. Square root of 2/3 plus 2/3 x cubed plus 1/3. There we go. Now, just like in the previous problem, I'm going to test whether I want to keep the plus or the minus because I can't have both using the initial value. So if I take the number 1 and I plug it in, I get 2/3 plus 1/3 is 1. The square root of 1 would be positive or -1. Since I want my answer to be -1, I would keep the negative in this case. So it would be negative square root of 2/3 x cubed plus 1/3 is my final answer. And again, I tested to see whether I wanted the plus or the minus by plugging in my x and seeing which one will give me a negative y. We're going to do one more of these together, and then we will save the last one for when I see you guys in class as a warm-up. So for problem number 3, it says, suppose dy over dx equals e to the x plus y. Find the particular solution to the differential equation if f of 0 equals negative natural log of 2. So my differential equation here is dy over dx equals e to the x plus y. Now, in order to separate the variables to get the x's and y's separated, I need to make sure that this x and this y are not both in the exponent here. I need like two separate things that have a separate x and a separate y. Right now, they're both contained in one exponent. So one of the properties that we know about exponents is that if we added our exponents, this was originally a multiplication problem. So I can say that this is equivalent to e to the x times e to the y. And again, one thing to remember here is that if you had x squared times x to the third, you would get x to the fifth because you would add the exponents. So if your exponents are added, you can separate this to make two separate bases so that e is still the base of both, but it's just to the x and to the y separately. So my new differential equation would be dy over dx equals e to the x times e to the y. Now it's much easier to separate my variables. So to separate these variables, I would divide by e to the y on both sides and multiply by dx. So I would have 1 over e to the y times dy equals e to the x times dx. The next step is going to be to do the antiderivative on both sides. So I'm going to integrate, which is the antiderivative. I like to rewrite 1 over e to the y as e to the negative y. It makes it easier for me to do my antiderivative. So the antiderivative here would be e to the negative y, but then I would need to divide by -1 because there would have been a chain rule. When I did the derivative, I would have multiplied by -1. The antiderivative of e to the x would be e to the x, and I'm going to remember to put my plus c so that I have a spot for that number. Now's when I'm going to take a detour. So I'm going to take my initial value, I'm going to plug that in, and I'm going to see if I can find the value of c. So when I plug in my numbers, I'm going to have -1 e to the positive natural log of 2. And the reason it's positive is that there's a negative in the equation, and there's a negative that I'm plugging in, and two negatives make a positive. And then I'm going to have e to the 0 plus c. E's and natural logs are inverse operations. So this is just going to be a 2, which means -1 times 2 is -2. E to the 0 is just 1 plus C. So C would have to be -3. Now I'm going to take that -3 and put it in to make my final equation. So I would have -1 e to the -y equals e to the x minus 3. In order to get y by itself here, I'm going to start by dividing everything by -1. So I would have e to the -y equals negative e to the x plus 3. Now, just like e is the inverse of natural log is the inverse of e. So to get rid of this e here, I would natural log both sides, which means I would have negative y equals the natural log of negative e to the x plus 3. And then to undo this negative that's in front of the y, I would just have negative the natural log of negative e to the x plus 3. And that's my final answer. Now, some students make a mistake here because they want to take this negative from the outside and distribute it. But you can't do that because these terms are inside of the natural log function, so we cannot distribute from the outside to the inside of a natural log. All right, we're going to go ahead and stop there for today. We are going to do a couple warm-up problems in class tomorrow, and then I'll give you guys some time to practice. So thank you so much for watching, and I'll see you tomorrow.